Welcome to our project presentation about reliability of binder jet printed Inconel 625 affected by binder burnout and informed by statistical methods. This is a collaborative proposal between myself, Marco Chmielus, and Satish Iyengar, and I am from the Department of Mechanical Engineering and Material Science, and Satish is from the Department of Statistics. We are describing here a project for 1 year, but we have a lot of ideas for a second year that are not presented here due to the time constraints. So let's look at why we want to investigate binder jet printing in Inconel 625. So Inconel 625 is a nickel-based superalloy, and it is used very heavily in aerospace, chemical, petrochemical, and marine applications because of its good resistance to corrosion over a wide range of temperatures. And here to point out especially is also saltwater corrosion. Binder jet 3D printing, on the other hand, is an additive manufacturing method that enables to print very complex shape parts with overhanging structures due to the support of a powder bed. But in contrast to other AM methods that use an energy beam to melt a powder, binder jet printing does not melt the powder during the printing process. It temporarily binds powder together with a printed binder per powder layer that then later gets cured and has to be removed again before sintering. So we want to really focus on this removal of the binder, and I will explain why that is. Excess or not burnout binder in our final part can form oxides and carbides and therefore influence the mechanical behavior and reliability of materials due to the formation of strain incompatibilities and stress concentrations that lead to cracking, especially under fatigue loading. Therefore, we need to better understand the effects of binder burnout temperature and duration and how they influence the mechanical properties and reliability of our parts. The objective of this proposal is to determine the relationship between binder burnout parameters and the residual impurities of sintered part microstructure and reliability, especially on Inconel 625. The deliverables are data sharing techniques for TGA data so that people are able to change sintering profiles and especially the binder burnout part of the sintering to adapt to specific binders and material. We want to share digital data files and imaging, linking process parameters to materials and the mechanical performance, and then share the statistical model for small data sets that were developed throughout this process. During the experimental part of our process, we will evaluate the binder, we will print parts and sinter them, which includes the binder burnout step. The sintered samples will receive a surface treatment to eliminate the stress concentrations on the surface, and then we will perform static and dynamic tests on these samples to evaluate reliability. Finally, we will look at the microstructure to investigate the impurities of the samples and also porosity and microstructure in general.
The statistical methods involve 3 main steps. The first is the planning and design, meaning that we will do a meta-analysis of the literature to summarize the relationship between input and the outcomes based on both the literature data and also our own data. We will then use design of experiments methods to identify gaps in the knowledge. Next, we will turn to factorial design methods to estimate main effects and interaction effects of the inputs upon the outcomes, and also do power calculations to determine experiment sample sizes to keep them as efficient as possible. Finally, we will use factorial linear models and to characterize the relationship between key inputs and outputs.
All the experimental tasks that are listed here are informed by the statistical approaches and models that are being developed from the beginning to the end of our proposed work. So thank you again for your interest, and please feel free to contact us with any questions.